and 0 that may be at the exascale. So these are my 3 slides for today. But obviously, the speakers will have much more to say and much more concrete ideas. So let me introduce first Aretha Teckentrup from Edinburgh. I don't know if you're able to share screen because I just stopped. Thank you. So Aretha, I give you the floor, the virtual floor. So learning functions from data. Thank you.
Yeah, thank you very much. So thanks for the introduction and thanks for giving me the opportunity to speak here. So what I want to talk about today is learning functions from data. So that might sound a bit mysterious at the moment. So I will explain what I mean by that. So the outline of my talk is quite simple. So I'm going to start by explaining to you the problem that I'm interested in solving. I'm then going to tell you how I'm going to solve it. So I'm going to solve the problem using Gaussian process regression. And then I'm going to tell you how well that works. So I'm going to talk about some of the kind of convergence properties and performance properties of the Gaussian process regression method. Okay, so the problem that I'm interested in solving is learning functions from data. So I have an unknown function f, which is just mapping from some domain U into the reals. This is an unknown function. I don't know what f is. The only information that I have about f are these function values. So I have my function values y, which consist of points, design points un, which are just points in the domain of f, and then the corresponding function values. And I have a finite number of them. So I have capital N of these function values, and I want to recover my function f from those function values. Okay. So this looks like quite a simple problem, but it actually appears in very many different contexts and very many different application areas. So as a search, for example, mentioned there's this topic of constructing surrogate models. So surrogate models, constructing surrogate models quite often falls into this kind of problem. Okay. So the way I'm going to solve it is using a Bayesian statistical framework. So by using a Bayesian statistical framework, you obtain as the solution to this problem a probability measure on the unknown function f given the data y. So that's what's called the posterior measure in the Bayesian statistical framework. So because you do obtain a whole posterior, a whole probability distribution f given y, that also allows for uncertainty quantification in the recovery. So you don't just get a best estimate of the function f, but you also have some information about how certain you are about this recovery. And so that allows for uncertainty quantification as well. Okay. The problem I'm interested in is what happens as n tends to infinity. So as the number of function values that we have tends to infinity, and in particular the question of posterior consistency. So whether we are able to recover the true function f as n tends to infinity. And in particular, I'm going to look at these two questions here. So I'm going to look at whether the mean of my posterior, so the mean of this posterior distribution that we have on f given y, whether that converges to the true function f, and whether the posterior variance goes to 0. So what this would mean is that the posterior measure, the probability measure that you have on f given y, kind of contracts around the true function f as n tends to infinity. Right. So as I said, I'm going to solve this in a Bayesian statistical framework. Gaussian process regression is just a particular instance of the Bayesian framework where you choose the prior distribution to be a Gaussian process. Right, so I'm choosing the prior distribution on my unknown function f as a Gaussian process. I'm choosing mean 0 for simplicity. You can do everything with non-zero mean as well. And then you have the covariance kernel. So if you're not familiar with Gaussian processes, I've put the definition here so that the function f is a Gaussian process. Now means that if you look at any point ui in the domain of f, then f of ui is now a Gaussian random variable. And if you look at any collection of function values, that is a joint Gaussian random variable. And the mean function gives you the mean. So in this case, I've chosen mean function 0. So the expected value of f at ui is 0. And then the kernel k that we have here is the kind of infinite dimensional analog of a covariance matrix. So it's a covariance kernel and it gives you the covariance of the function f evaluated at different points. Right. So more visually, you have something like this. You define a mean function, which here I've chosen to be mean 0, and then you also have a kind of covariance function, and in particular you have a variance at each point, so you have a standard deviation here, and then if you look at samples from this Gaussian process, you will obtain functions that look something like this. So they stay close to the mean, which here is 0, and then they fluctuate around the mean. Okay, so that is our prior. So this is the prior that we put on the function f before we observe any of the data. Right? And then once we have observed the data, we do the usual step in the Bayesian framework, where we condition the prior on the observed data. So we take our Gaussian process prior, condition it on the observed data, which in our case were these function values. That gives you the posterior distribution on f given y. Okay. So the nice thing about Gaussian processes is that this step can be done completely analytically. So in this Bayesian framework, you could choose any prior distribution that you like, but the nice thing about the Gaussian process priors is that you can do this conditioning completely explicitly. So you know that the posterior is also a Gaussian process, and you also know explicitly what the mean and the covariance functions are. So I've written them down here. Exactly what they are not that important for this talk, but you have the explicit expressions here as well. Right. So again, visually, what you're now doing is you're observing some function values, say at these points here, where we have our dots, and then you're conditioning everything on passing through those values. Right? So then you obtain a mean function, which also passes through those values. At those values, you then have a standard deviation of 0, because you know at those points, you know exactly what the function is, so there's no uncertainty there. And then you also get sample paths that all go through your function values that you have observed. Right. So you might think that that's the end of the story, right? I told you I wanted to obtain my posterior measure on f given y. I've shown you how to do this. I've told you you can do all of this explicitly. But there are a lot of, there's some things that you have to think about. So one of the main challenges is to actually choose the prior distribution. And so the way that you choose the prior distribution is that it needs to reflect properties of f, right? So the prior distribution has to be a probability distribution that makes sense for the function f that you have. And so it needs to include anything that you know about f. Right? So it has to include information about these things that I've listed here. So one of the things is the smoothness of f. So how many derivatives f is going to have. So by smoothness, I'm going to mean the number of derivatives it possesses. Right? So yeah, so there's usually a hyperparameter in the prior which governs this. And so I've given you some examples here. So in the first row here, I've plotted some samples from a Gaussian process, which is only Hölder continuous with exponent 1/2. So you see that you get quite rough sample paths, whereas here I've plotted samples from a Gaussian process, which has analytic sample paths, so sample paths which are infinitely many times differentiable, and you can see that you get a lot smoother functions. And the prior that you choose, or in particular the covariance kernel K that you choose for the prior, also governs the contrast. So by contrast, I kind of mean the amplitude of the fluctuation, so kind of where it lies on the x-axis, so how big the fluctuations are that you get. There's also kind of the horizontal length scale, so the length scale of the fluctuations. So that is related to how many oscillations or how many fluctuations you expect. So again, if you look at these plots that I have here, these in the first row, the plots, or particularly this one, has quite a long length scale. And so the lambda here is a length scale parameter for these fluctuations. The lambda here is quite large, and you see you have quite smooth functions, and they only vary on a large length scale, whereas here the length scale parameter is chosen to be smaller, and you do get fluctuations on a much finer length scale. right? So all of this is typically controlled by the prior, in particular some hyperparameters or parameters that appear in the prior. Usually the covariance kernel also influences other properties such as periodicity, so whether you have periodic sample paths, and also stationarity, so whether you have the same behavior in all parts of the domain or if the Gaussian process behaves differently in different parts of the domain. But I'm not going to talk too much about those two today, and I'm mostly focusing on these kind of things here. Yeah. So all of that is determined by the prior, and the problem is that you don't really know these kind of properties a priori, right? So you don't know what the function f is. All you know about the function f is these function values that you have, and so you typically don't really know, for example, how many derivatives your f has, or what the kind of typical length scales are that you expect, right? So that is one of the big challenges in using this for a broad class of functions f. So there's different approaches that you can do to deal with this. So in a fully hierarchical Bayesian approach, you would have to integrate out the unknown parameters. So here my theta are the hyperparameters that appear in the prior. So the theta would be parameters that govern things like this. So the smoothness, the contrast, and the length scale. In a fully Bayesian hierarchical approach, you would have to integrate them out, right? So you obtain the joint posterior of f and the unknown parameters given the data, and then you integrate out the theta. The problem is that that is most often intractable, so you're not able to do that integration exactly or even well numerically. So another thing that you can do is empirical Bayes, and that's what I'm doing in this talk. So I'm going to estimate the value of the hyperparameter from the data. So I use the data that I have observed, and I estimate the value of the hyperparameters from it, and then I'm going to cheat a bit and pretend that I know the value of theta. So I'm going to take the estimated value of theta and say that is my true value of theta, and then just plug that into the prior distribution as the known value for the hyperparameters, and then do the standard prior to posterior update. The way that you estimate the hyperparameters is not really important for what I'm going to show you. You can do very many different things. So there's usually a difficult question on its own, and you can do something like maximum likelihood estimation or cross-validation or whatever you like, really. And then again, I'm interested in posterior consistency. So what happens as n tends to infinity, right? So as we get more and more function values. So just to recall, so what I want to show is that we get posterior consistency in the sense that the mean of the Gaussian process posterior, so the mean of my posterior distribution on f given y tends to the true function f, and the variance of the posterior goes to 0. Right? So then the posterior concentrates around the true function f. And to prove that, we can actually use some results from numerical analysis. So if you look at the equations a bit more carefully, what you see is that the mean of my posterior is a linear combination of the kernel functions. So the k here was the prior covariance kernel. And if you look at the explicit expression that you have, you can show that you can express it as this linear combination here for some coefficients alpha that you know. And you also know that the mean is an interpolant, right? Because we're conditioning on these function values. We know that the mean always goes through these function values, right? So that was seen from this picture here, for example. You're conditioning on the function values that you have. So the mean will always go through the function values. And so the mean is really an interpolant of f, right? It interpolates f at your design points. And it's a kernel interpolant. So the kernel just here means that you have these kernel functions as the basis functions. And so in particular, if you have an isotropic kernel, which depends on the two inputs only through the distance, then you have a radial basis function interpolant, right? So radial basis function interpolants are something that are well known in numerical analysis. Okay. So once you have these properties, so once you know that the mean is really just a kernel interpolant of your function, then you can use known results from scattered data approximation and radio basis function interpolation. The convergent properties that you get will depend very much on the specific choice of the covariance kernel K. Right? So the K here now takes the role of the basis functions. Right? So your mean here is an interpolant of F. It's an interpolant in the specific basis functions K. And so what kind of convergence properties you get will depend very much on what your K is. And there are results out there for a wide variety of different choices. Right? So I now wanted to show you two specific examples. So one example is the family of Matern covariances. So this is something that some of you might have seen before. If you haven't, it's not that important. So this this family has three different hyperparameters. So there's the sigma squared parameter, which is the marginal variance. So that is kind of the contrast parameter, so the one that governs how big your oscillations are, the amplitudes of the oscillations. Then you have the lambda, which is the length scale parameter, so the one which governs whether you have kind of just long scale oscillations or very fine scale oscillations, so it's the typical length scale. And then the third parameter is this mu, which governs the smoothness, so how many derivatives your function f is going to have. Right? So in general, this looks quite complicated. So you have the gamma function here. This is the modified Bessel function of the second kind. It does simplify in some cases. So depending on what the parameter nu is, if nu is equal to 1/2, you get the exponential covariance. You might recognize this as the covariance of the Ornstein-Uhlenbeck process. And if nu is equal to infinity, or in the limit as nu tends to infinity, you obtain the Gaussian covariance. Right, so those are some of the examples. But in general, you have these three hyperparameters, which you would then need to tune to reflect the properties of your function f. Right. So I now want to show you a convergence result as n tends to infinity. And for that, I need to define these two things. So the first one is the fill distance. That's also known as the maximum distance. Some people call it the separation distance or dispersion. So it has a lot of different names in different communities. So this is what I call H. And H is really a measure of how space filling your points are. So you have your design points Dn, so these were the points where we had our function values. And if they are very well spread, so if they cover your domain U quite well, then the H is going to be quite small. Whereas if you have big gaps somewhere, then the H is going to be quite large. Right? So you're taking the maximum distance that any point U can be away from any of the design points. Right? And typically this fill distance will go like n to the -1 over the dimension. So if you have capital N points in a du dimensional space, then this fill distance will typically go as n to the -1 over d. Right? So it's a measure of how well you're filling the space, and yeah, if there are any big gaps anywhere. Right. The second quantity is this mesh ratio, so that is the rho. This is something that is related to stability. I'm going to come back to that. It is, in a way, a measure of quasi-uniformity. So it doesn't just look at how space-filling the design is, but also how uniformly spread everything is. So if you look at it in the numerator, you have the fill distance. So this is the same thing here. And then in the denominator, you have the minimum distance between two design points. So in a way, you have in the denominator the maximum distance between points, and in the denominator the minimum distance between 2 points. And so this rho n really measures whether the minimum distance and the maximum distance between 2 points kind of go with the same rate in n, so whether you have kind of a quasi-uniform mesh. Okay. Right. So the result that we have is then this one. Okay, so it's a bit complicated, a lot to take in, but let me try and walk you through it. So I have a result which shows that the mean of the Gaussian process posterior, so this is the mean of the probability distribution on F given Y, you can show that that goes to F in the L2 norm with this rate in N that's going to come from here. And for the variance, you can show that it goes to 0, again with a rate in N that will come from these terms. This result holds for any function F that has this smoothness here. So I'm assuming F here is in this Sobolev space of smoothness nu plus d over 2. And as I said, the convergence in N really comes from these terms here. So the first term here is the one that is related to the fill distance. So this is the term that is decreasing in N, and this really comes kind of from the convergence properties. So as you fill more and more points into your space, then the error between F and the mean goes down. And so when you're kind of filling up all the space and the fill distance is going to 0, then you're kind of recovering the true function F. So here you get a convergence rate in N. And then you have this term here, which is related to stability. So this is only, it's something that comes from the stability of the method. Essentially, you can have stability properties if you have 2 points which are very, very close together, and that's where this mesh ratio comes in here. Okay, so the nu star that's appearing here is the estimated smoothness, right? So the nu here is in a way the true smoothness parameter, because it is the true, it's the smoothness of the underlying function F. And then the nu star here is kind of the smoothness that you're estimating from the data. So your estimated smoothness parameter, that you're estimating from the data, and then the rates depend on kind of the relationship between the true smoothness and the estimated smoothness. Okay. If you are able to estimate your smoothness correctly, then you obtain optimal rates. So this is the rate that you get when you figure out what all of this is, and you're estimating it correctly. So those are optimal in the sense that they are optimal for any function F from this Sobolev space here. As I said, this the rho n term, the mesh ratio term here, is related to stability, and you see that this stability term here only comes in if your estimated smoothness nu star is greater than the true smoothness nu, and that is because you then have stability issues. So in this case, what you're doing is you're approximating a function F by basis functions K, which are smoother than F. So the basis functions that you're using in your interpolant are smoother than the function that you're trying to approximate, and then you can have some stability issues. Right. This result does hold in a very wide variety of cases, so you don't really have very many assumptions that you need on your estimated parameters. And that's, again, as I said, you don't really need to know much about how you estimate the parameters, whether you use maximum likelihood or whatever you want to use. All you need is that these estimates are uniformly bounded away from 0 and infinity, and you also don't need them to converge. So I've written it down here where the case where you do converge, but you can equally also just work with the lim sup and the lim inf. And in particular, the only important quantity is really the smoothness, because that's what governs the convergence rate. The estimated length scale and the estimated contrast just go into the constant. Right. So now I'm almost out of time, but let me just very quickly show you the next result. So the problem that you have here with these rates is that they deteriorate very quickly with the dimension. So here in the rate, you have the 1 over the dimension coming in. So that is because of the assumption that you're making on F. So if you do have a function F that is just in this general isotropic Sobolev space, as I said, these rates are actually optimal. So you cannot do any better. So if you do want to get faster convergence rates, which don't deteriorate with the dimension, you have to make stronger assumptions on F. And in particular, if you move to spaces of dominating mixed smoothness, then you can get faster convergence rates. So these spaces of mixed dominating smoothness are tensor products of one-dimensional Sobolev spaces. Okay, so it's still related to Sobolev spaces, but it is a slightly stronger or much stronger assumption on F. And essentially what this gives you is you have much stronger control on the mixed derivatives, which where the name comes from with this dominating mixed smoothness. Right? So because you're assuming that your F is in a tensor product of one-dimensional Sobolev spaces, you then also use a kernel, which is a product of one-dimensional kernels, and you have to assume that you're working in a domain, which is a product of one-dimensional domains, but then you can actually show that you can get faster rates. So this theorem here, I do have a very explicit version in the paper. So here I've kind of tried to summarize it just to get the main point across. So I can give you very explicit expressions for this rate alpha and the alpha prime here if you're interested. But the main point here is really just that by moving to this smaller class of functions F, so by imposing stronger assumptions on F, you can actually get a rate in N which does not deteriorate with the dimension. So the alpha that you get here again depends on the true smoothness of your F and the estimated smoothness, but it is independent of the dimension. Right? So we don't get this problem here that the rate goes to deteriorates with the dimension, but you do get something that is independent of the dimension up to this log factor here. So you do still have this log factor here that depends on the dimension, but this rate that you get here is independent of the dimension. All right. So that was really all I wanted to say. Have some conclusions here, which I mean, the only thing I really always like to point out is that you really don't need very strong assumptions, and you don't really need to estimate your hyperparameters very well in order to still get posterior consistency. So you do still recover the function F as n tends to infinity, even if you do include the learning of hyperparameters and you have some misspecification in the prior. So let me then just point you to this paper that I have on arXiv, and that is going to appear in the SciAm Journal of Uncertainty Quantification. Okay, thank you very much for your attention.
Thank you so much. So we may have some questions, but I think people are shy, or maybe they're struggling with the system. So there's a Q&A button at the top or bottom, wherever you are in Zoom. So while people log their question, I have a question, if I may, Aretha. So n goes to infinity means you have many, many more evaluations of the function. So this is maybe enabled by the exascale if we can manage to, launch a large number of runs. So you have that aspect, but you also have this aspect of the design, as you say, the stability and all these issues if they happen to be close to one another in some way, or the points in the design. I mean, you mentioned this possible instability. So how to trade this off? Because the computational cost of running all these runs of the simulator is going to be large, but the gain is there. You can quantify the gain. What do you foresee in terms of practical implementation of this on an exascale computer? That's a big question.
Yeah. Yeah, I don't know. I think it's so as you said. I mean, in general, theoretically, right? It should be better to always increase n, right? Because you expect to always, well, you would expect the error to always go down with n. But as you said, at some point you might run into numerical stability issues. I think the numerical stability issues are going to be quite difficult to detect. So I'm not sure. I guess you would have to have some way of detecting those, which I'm not really sure.
Yeah,
I mean, I guess in principle, you should always have as many data points as possible, right?
Yes. There's a question in the Q&A, very nice talk. Can you say what happens if you do not make the perfect model assumption? That is, the observations f of u has errors, random. Can this all be extended to this case?
Yeah, so there are some results as well for for noisy data. Yeah.
There's another question in the chat, or maybe you were not finished.
If somebody wants a reference on the noisy data, then please send me an email and I'll be happy to.
Another question by Peter Challoner. Do you have equivalent results for the rate of convergence of the marginal variance to 0?
So
we can also sorry, yeah, go ahead.
Yeah. Sorry, what is the marginal variance? Can you? I'm not quite sure exactly what quantity you're after.
That's the question. There are two more questions. So the best thing that what we did yesterday would be for you to be kind enough to type the answer in the Q&A. I think you have this option as a speaker if you look at the Q&A while the next talk
okay, yeah,
is being delivered. Yes, there's another question from Malgorzata Simon and another question from Nancy Nichols. So, and maybe you could even interact with the person asking the question if you have questions about the question.
Okay, yeah, I can do that.
But that was very nice. Thank you so much.